Okay, John, what are we doing here?
We're going to test these rocks for transistor properties. And so if you come over here a little bit, we're going to use this plate for the negative, the emitter, which should normally be the emitter on the transistor. And of course the curve tracer is going to show us the gain. But first, we know that the rock is not, it's full of impurities. So the reason for me testing this is because Tesla knew this also. He knew that to get the energy that you needed, there had to be crystal lattices, and it had to be sort of semiconductor properties. So if you look right here, we're going to use this for the emitter. And see the red one here? We're going to call this the collector. We're going to stick this rock and see. We get like a diode action. So we're going to get it to sit on here. And we're going to get that action. And then we're going to use this as the base. And then you can see when we hit the right point, we have a semiconductor.
So what are you doing down here when we're doing that on the screen? You're just kind of...
Well, I'm doing like, I'm touching a contact here. So now there's 3 leads.
So,
like,
so these are just random points on the...
yeah, random points on the rock, and we're looking for the best gain.
And the rock is what, iron pyrite?
Yes, it's iron pyrite here. Now watch, here between this sample and this one here.
So we change rocks here.
Mm-hmm. And see, this one's totally different now. See?
So you have a what, resistor there?
Yeah, see, and if we change the gain.
So the first time you didn't have a resistor?
No, we're just using this resistor lead for the contact.
Oh, I see, okay.
And see here, now we're getting the curve like a transistor, see? So that means if we make a semiconductor out of it, it'll stay just like a transistor with gain. See? Almost like a Fogel device almost here. See here? Now let's change the device.
So this is back to the first rock.
Yes.
So you're touching the rock now.
Yeah, see, that one's completely different. See, and it's sort of like they did with a crystal radio early on, detecting energy.
The cat's whiskers?
Yes. And so, see, we could make a device out of this and probably use it in real high frequency, like for capturing the cosmic rays.
Is that what Tesla was doing?
Well, Tesla knew about this, because he talked about the crystal lattices. And this is nothing more than a crystal lattice. So here's a real transistor. Right here. And you can see just how much the difference is in gain. See here? But that's got solid points. In other words, that's bonded material. There's solid points, and so this tells us the gain of the device. So if we take another transistor,
Okay, so you're changing transistors now.
I'm changing transistors, and you can see that this is a modified transistor. It's more like the rock. See? It's more like the rock. Now we'll
So
just,
what model of transistors were these two?
well, these are audio power transistors, but one's been modified by us to look for a different gain ratio,
Okay.
a different frequency response. And you can see with the rock, we use the aluminum for the emitter, and then we'll just use this for the collector. We use a piece of wire for the base. So you notice right away we have a junction. And see, when we get this where we want it, then we get a transistor. More in the high frequency end here. See? See, and by moving it around, we could choose the point, the actual frequency that we want to capture by moving it around. You can actually tune it. There we go. So that's how simple a semiconductor is. That you could make it out of a rock if you had to.
I know Tom Bearden said the early transistors, the point contact transistors, were all nonlinear.
Yes, that is nonlinear.
And would also gating energy from the vacuum.
Yes, that's exactly what they did. Because see, here's a standard transistor, watch. This is just stock, you can buy it off the shelf. See, you're fixed. You're fixed. You can't do anything with that device. But the rock, you can.
Oh,
See?
yeah. Yeah.
This is very linear.
Yeah. You're locked in, and that's its one curve.
That's its one curve, because
Yeah.
if we change devices, if we just take a device out here, let's see what we got here. This could be bad, they could be good. But if we take another device, see, it's a different curve. So you're locked in to that curve on that device. You're locked into this curve. On this device. See? But watch the rock. See, we can move the point contact around, and we can go as non-linear or as linear as we want. See, once we hold it solid, then it stays.
So you can pretty much tailor that to do anything that you want to do.
Absolutely.
So that's why, in many respects, that would be more an advantage, more of an advantage than just using a conventional manufactured transistor.
That's correct, and this wouldn't burn out like a normal transistor. And besides, we'd be using this for a detector. we'd be using this to detect the cosmic energy that we want to capture.
What do you mean by cosmic energy?
Well, the radiant energy,
Okay.
vacuum energy. Here when Tom Bearden talked about the nonlinear properties of these devices.
So Tesla was knowledgeable about this particular
Yes, he was,
characteristic.
because he absolutely said that he knew that the answer lied in these crystal lattices here of the structure of the material. So in the later years of his life, he worked very hard to discover and build these energy machines that were very small benchtop type power supplies.
Have you used these rocks in your own machines?
Yes. Yes, we did. We manufactured, this is what Tom Bearden's talking about, many different crystals that we tested for these type properties. We made capacitors, and you can see the crystal here. We actually ground up rocks and made our own transistors. You can actually see it here. These are copper substrates, oxygen-free copper. And of course, if you had a microscope and you can see they're all numbered on the back, because we tested each specific crystal. You can see the crystal structure.
Yeah.
So
how long ago did you make those?
probably during 1982 is what Tom Bearden's talking about when he says, well, he used to run all over and collect rocks and grind them up. And this is some of the work. This is just a leftover box, but this is just some of the work of some of the transistors. You can see there's resistors on this that we did. Each one had its own property. Here's another one. And then we built a die and a press, and you can see this is diatomaceous earth in here. It's been pressed in at like 5 tons or 10 tons.
Wasn't that what Henry Moray called
Yes.
Swedish stone?
Yes.
So Henry Moray also,
He knew this.
yeah.
Now here's one that's been broke off, so you can see the crystal structure. Actually, here's the other side of the crystal. You can see that each one formed at each temperature gave us a specific crystal structure.
So how would you make these?
In an oven at 4,000 degrees in a kiln, we'd grind up the material into a powderized form. Then, of course, you have a blank slug and a piece of copper, like this, just basically a piece of copper. You put the material in between. You put this in the oven. You fire it at 4,000 degrees, and the rock melts into a crystal and forms a semiconductive material, and then this is what you get. So you could probably call this the collector, call that the emitter. See, it's straight up. Call that the emitter, and then probe around. But see, this isn't going to be like the rock, because this is already bonded.
Right.
So right now it's just got a different structure to it. And if we could get it, you see, this is actually Probably not a good thing to do, because this isn't like this right here.
So you're back with the iron pyrite right now.
I'm back at iron pyrite. See, because I can get, well, as soon as I get in here. See? I can tailor my semiconductor here by making a point contact out of this. So I could actually grind this, grind a point contact, come down and stick it on it, and I'd always have this device. And as long as I did them all the same, on the same machine, precisely, I would have this semiconductive device each time.
Why aren't the big manufacturing companies not using these characteristics?
Well, they do.
Oh yeah?
They did. That's the whole idea, is they're doping their materials. They're taking pure silicon and doping the material to get their junctions. And because they want a linear device, they want a device that they can manufacture very quickly, that always comes out the same way.
Right.
But you're stuck with this.
Yeah, yeah.
Because this isn't going to change until it burns out here.
But wouldn't there be certain situations where they actually, or having a dynamic capability would be more advantageous for the particular application?
Well, sure, but that would be like tunnel diodes, and it would be like in microwave and, you know, solar cells and things like that, where they're a specific structure.
Yeah.
But
So
what I was doing here was testing the properties of all these crystals.
When you fired these in the oven, John, were there any other interesting phenomenon that went on?
Yeah, when you look at the back side of this, let's see if I can get one here. When you look at the back side of this, if you look very closely right here, that's gold. And it's sort of a ruby crystal with the gold in it. So if you could get this under a microscope and look at it, that's exactly what you'd see, is an electrical conductive gold in crystalline form.
So you were actually doing transmutation?
Yes, that's what I was actually looking at. And the way that you transmutate it was with the heat. So you can actually see it in there. It's got a gold luster to it with the ruby color. Maybe I can get a glass and you can...
How do you know that's gold?
Well, because I had it analyzed. I had it assayed. And you might be able to see this. See? So you actually can see it better right here. See? Where I'm scraping it? Mm-hmm. Sort of a gold color, see it? It's embedded in its own crystal structure.
Huh. So you stumbled into this as a byproduct of producing these.
Exactly.
And then you had them assayed and you found out you were actually making gold.
Right, I had all this material assayed, and because I was using this in the hi-fi industry to run sound waves through. Then if you took this crystal substrate and you placed a dot here, and you put the sound here, and you placed a dot here, and you placed a dot here, right?
Hold on. Right.
See, each one of these lattices, then that becomes a crystal, has a different pathway for the sound to go through. So you can basically position the sound and the frequency of the sound wherever you want it.
And what does that do for you?
Well, I used it in the audio industry to do like pseudo stereo monophonic sounds and
Okay.
frequency crystals that I could use for a filter. And so that's basically what started me off on all this. And then, of course, I discovered that there was this sort of transmutation process in the oven that was taking place.
Did it surprise the heck out of you?
Oh, absolutely, because how could you get, you're just using copper and you're using lead and iron sulfide. But then what happens is all this material is already in here.
Right.
And so what you're doing is the frequency of the oven and the heat, you can sort of transmute one piece of material to another. And of course we put all this on after that. You solder the leads
Right.
on and everything. You had to file it because it becomes very difficult after that. And as you can see, it makes up the crystals that Tom Bearden were talking about, that energy comes out of. Because if you stress this crystal, then you can get energy out of it. It's sort of piezoelectric.
Which is what Murray was doing when,
Yes.
when he was pressing them with railroad presses?
Yes.
T. Henry had a process where you could go out to quartzite sand, good quartzite sand, and you could dig yourself up a ton of quartzite sand. You could run it through his process, and it'd make about 100 ounces of gold, depending on the time and everything, 50 to 100 ounces. You could take the quartzite sand you just dumped out that you processed, as if you had gold in it to begin with. You could run that right back through there, and you'd get another 40, 50 ounces. So that was one of the reasons that they were coming down on him to kill him and everything like that. The last thing you want to do is make gold. Bedini made gold, and we almost got killed. One of the great disruptor, Sajeka, may he not rest in peace. The silly bastard is dead now, and good riddance, because he was responsible for deaths of some folks, and he suppressed an incredible amount of free energy machines and stuff. And he's very proud of his handiwork. Well, Sajeka was sent in to suppress the effort. We didn't know who the hell he was, except he had all this information, all this knowledge. Because everything he helped suppress and all, he meticulously documented it with slides and photographs, and you can't believe the documentation. And his modus operandi was, he had been briefed that John had ground all these rocks, and so John was a natural. See, I'll sell him on how to make gold, but I'll hold back 20% of the process. What he didn't know is that 20% he held back, John already knew. The other mistake he made, he thought I was the brains of the outfit. I wasn't. John was. I don't know a damn thing about grinding up rocks. I'm not a bench person. John is, and he's an awfully good one. So in John's making of his transistors for his audio amplifiers, he puts them under pressure, very high stress, and he centers them, not too different from what Moray does, and he fires electrical discharge, huge electrical discharge bursts into them. And when he gets through, he makes these beautiful transistors, but the slag that's left over from what he started with has turned into black ruby laced with gold and silver. Prettiest stuff you ever saw. Beautiful stuff. And there wasn't any ruby in there to begin with, and there wasn't any gold, and there wasn't any silver. So John proceeded to take this process he did, add the other 20% and make gold, and Sajeka almost came unglued. Because he came in, and here we were, we're going to open up a mine called Bedini 1. We're going to assault that sucker at midnight. We'd already had the stuff assayed. John had had it assayed. It was real gold, no question. By the way, when you make a transmutation of gold, all the isotopes of gold have very short lives. Wait 30 minutes while it's radioactive and it all goes away and you don't have any problem. So that's one big benefit. So Sajeka hurries and scurries out of there because we're going to open up a mine. We're going to fund the energy work, but Bedini 1, a mine. And we're going to dig it out, let some guys dig it out, and we're going to sell the gold, you see, just like it was ore. But we're going to plant it every night. So he goes out and he makes a call, and he's back in less than 24 hours, and he even dropped some of his cover. He let us know who he was talking to. It was very interesting that was part of the channel. The guy was a well-known scientist. But we were ordered, you've got 24 hours to agree to quit this or you both will be killed. You will be killed. You can play with your silly little energy stuff, but if you think you're going to make gold and play with the international finance, you got another thing coming. For your silly information, half the gold the Russians sell on the market's made in the lab, but you're not going to make it. Well, actually, they meant business. They said, if either one of you guys gets on an airplane or travels, in 60 days, you will die. We won't tell you where we'll kill you on the airplane or getting on or off, but you will die. So 60 days is it. And meanwhile, you got 24 hours to agree to give this up. So we did. There's no need to commit suicide. Well, about 64 days later, I had to travel. Oh, by the way, they said, and Bearden, we may kill you, thinking I'm the brains behind how we made the go. I'm not. John is at all. But it took the pressure off of John, see. So we may kill you anyway. We're still making up our mind on it. And they're arrogant bastards, you see. If we do, it'll be by an ice dart dipped in curare. Big mistake. The fellow who invented that trick for the CIA happens to be a personal friend of mine. By sheer coincidence. They didn't know that. I knew all about ice darts dipped in curare. So, anyway, 64 days later, I had to make a trip to El Paso. I carried a government PhD with me on the project we were working on. We went out there and did our business. Come back on American, you come back through Dallas-Fort Worth, change to another flight, come to Huntsville. We got in about 5 o'clock in Dallas-Fort Worth International Airport. You know what it is there at 5 o'clock, all kinds, hundreds of people walking. And in those days, they didn't have the phones back on the wall. They had them on up there right by the walkway on a little board outfit with little ears on it. And you just step up and take the phone and talk. Now they got to move back on the wall. But the fellow that got off the airplane ahead of me, a few steps ahead of me, walked in and picked up the phone off the little ear, stopped. And I stepped past him one step, and he let out a squall and hit the floor, kicking and flopping. And I knew what happened. I moved very suddenly, getting my back to a pillow. I never did see the guy fired the shot, for too many people. But I sit there and watch the guy kick and flop and bite through his tongue and start bleeding out the side of his mouth and die. He just flat died right there on the floor. And Dr. Kelly had gone to the John, and when he came, I wanted to witness to the incident. So when he came out, I said, Dr. Kelly, I think this fellow had some kind of seizure or something. Looks to me like he just died. And Kelly went up and looked, and there's other people beginning to gather around, and he says, he is very, very dead. He ain't breathing, nothing. There's no pulse you can see anywhere or anything. He's dead. So I said, let's get the hell out of here. I never did tell him what was involved. But then here come the emergency guys, with their instruments and everything, running like hell and with a stretcher and all this. But they did. They killed this guy who I didn't know from Adam's off Ox. I never met him, and he didn't know me, had no connection with me. But he was a convenient target to use to prove to me they meant business. They killed that poor guy with an ice dart dipped in curare, just like they had said, just to teach me they meant business. And, that's the kind of mentality and the kind of people you're dealing with.
You don't think they were shooting at you and missed?
Oh, no. They wouldn't send anybody. It's too close a range of weapon. You don't use an ice dart from a gun. See, what you do if you use it with a gun, you use a sabot carrying bullet. It's got it actually is a little dart made out of ice. It fits in this sabot in the end of the bullet. And the bullet has got a calculated amount of explosive in it. And when you fire the bullet, the sabot runs down and hits an obstruction and stops, and the ice dart goes on out in the air, and it's been dipped in curare. And this ice dart comes in and hits you, penetrates. The curare paralyzes your lungs and your heart. Your heart will stop beating, and your lungs will stop breathing, and your body goes into violent convulsions, fighting for air and everything. And you might break a bone, or you might, bite through your lip, or what. There's some kind of symptom usually goes with that kind of seizure, of convulsions, and so the person dies. And the ice melts, and curare breaks down very quickly in the body. Unless you've got the world's best experts testing it, they'll write that the guy died with normal heart attack or convulsions. The autopsy will not show anything, murder or anything like that at all. So they killed that guy just to teach me a lesson. That's the kind of really bad people at that entourage level I'm talking about, who do the enforcement if it has to be done. We did not make the gold, I guarantee you, and we never went back and tried again. We knew better than to do that.
And that's basically what we did with these right here. We could make any resistance we wanted to, but a resistor that doesn't burn out. We could actually put power through here. See if you look here, Tony. You see here?
Yeah.
Look at the resistance here. And they would always come out the same. See, 0.257 k ohms. Go down.
So we're measuring the resistance
Yeah, you're
of...
measuring the resistance of that particular pressed crystal right in here, see? If we
Okay.
break it loose, where you can see this. This is actually the material in the rocks pressed. And if you put it down here, you can see that that's the material. And that's what gives you this resistance here. So we're analyzing.
Hold on. Just
No matter what I do with it, you see it still maintains around the same resistance.
And how many ohms is that?
0.2443 kiloohms. See, if we go and we measure around like this one here, see up there, it's totally different.
.4469
Yeah.
kilo ohms.
Yeah, see here? And if we took, where you're not going to get this, if you take this lead, touch it here, and then bring it down on the crystal. See here, look, 0.
0.02.
Yeah, so this is sort of like, if I cross-hatch these, I'd have something very similar to Chung's negative resistor.
Oh, yeah.
You see what I'm saying?
Yeah, yeah. So then,
If I took
we'd be
these-
talking about radiant energy and negative...
Resistance. See?
Yeah.
And the thing is, if I cross these, if I took the material and laid it this way and fired it, right? And then I took some more material, laid it this way and fired it. And then I took some more material, laid it this way and fired it. And I would have that same junction
Right.
that she had with her pressed carbon. But I would have done it with these rocks, which this is all natural, so it's already got the doping in it.
Right, right.
So that would have been my semiconductor. And of course,
Fascinating.
we built all different kinds to look at different properties. What happened if we ran a bar this way and a bar this way, see? And we could get all these different properties. Like, see, look at this one. 0, 0, 0.
We just shoot this here, what we've got going
Yeah,
on.
see here, I'm just looking across the junction. See, now if I go to this junction, look at this one. Pretty soon I'll go negative with it. See?
Oh, so you're actually gating in energy.
Yeah, right, exactly.
So you have a negative resistor right there.
Well, basically, room
Yeah.
temperature semiconductor.
Right.
See? And we used to use these so that we could hook them up for sound. See, this one says quartz, Q,
Right.
quartz crystal. So this is a quartz crystal that's been pressed and mixed and fired. And basically, I don't know if your camera can get up here, but you can see the material in between here. You can see it's shiny.
Good picture. Yeah, it's good. It's right underneath the.
You can see it.
That's quartz.
That's quartz.
Okay.
So we wanted to see what it did to the actual, what we were looking for was a room temperature superconductor with barely any resistance at all, and you can see that here.
Well, it's certainly 0.003.
Yeah. So it's going to go negative.
Yeah.
You follow me?
Yeah.
When the electricity hits it, it tries to go negative. See here, we're on this electrode now, on this one. See, that one's, it's going to follow suit here.
That one's not quite negative.
Yeah. So that's basically what we were doing. This is what Tom Bearden talks about, where John's running all over the desert collecting rocks. He's measuring rocks. He's trying to get all these rocks that emit. See, like this one?
That was negative there.
Yeah, see? See how close this one is to this one? Because these were fired from the same batch. They're both quartz.
Okay, well, just to recap, go from the bottom up what we've got here.
Well, this one here, see, we need to go to an electrode, right?
Right.
So we're going to use this as a substrate.
This being what? What's it made out of?
Copper. This is oxygen-free copper, and then the material's put in this little milled out slot. See here? There's a slot here.
Okay.
And then, of course, this piece is oxygen-free copper, and it was machined so that this piece went into the slot and then fired at 4,000 and 5,000 degrees. And so what you get is this is what you get, and they all come out the same. Now, when you run sound through this, right? When you put sound through this, the sound changes.
Huh.
Because you're running it through a semiconductive material, but it's not a diode.
Yeah.
So, if you look at this one, we'll see what we get out of this one. See? So this would be a much higher resistance to the sound. See? And then once again, that material's been pressed in.
Right. That one was not fired?
No, these were pressed.
These were pressed, okay.
With a 5-ton press.
Okay.
The fired ones actually, you can see right here.
So do only the fired ones exhibit negative resistance?
Yes. Yes, and I think it's due to, see, like here, I'm using a point contact here.
Right.
So that's just when Tom Bearden talks about John running all over the desert, collecting rocks and measuring rocks. This is exactly what I was trying to do. Was I was looking for room temperature semiconductors that would emit energy.
Okay, what are we going to do?
We're going to test this for negativity.
Okay.
And so the meter will jump backwards for a minute. When we get it just right on the crystal, and you can see it went negative.
Right.
So it goes to zero resistance and comes back to the positive domain. There it goes.
Got it.
See?
Yeah.
And so that's this. That's the quartz crystal in here that we made these ionic tubes out of. So let's do it again. There it goes.
Okay. Good. So what's the significance when it does flip negative like that?
Well, we want to see the crystal go into the negative end and then come out with a positive. So that because the energy that we want is positive.
if you put a stack of those in series or parallel, could you produce like commercial power from them?
Well,
As in,
that's what I was after. I'm after collecting what Tesla termed the cosmic rays.
okay,
And I need a special lattice that collects that energy, and then it's like a one-way gate valve. We want to gate that energy one way, and it can't return. So it's just going
Right.
to fill a capacitor and keep filling that capacitor. And it can't ever come backwards.
so here you don't need to do any pulsing or anything like that.
No.
It's already built into the
No,
apparatus.
we just have to find the right material that's going to gate this energy, and then so I worked on this and found out you could make semiconductors out of it, and diodes out of it. And it's like an early crystal radio. That's actually what Moray had, was a super crystal radio that was tuned into the universe. That's basically what he had. So that's just a little insight into when Tom Byrne says he spent all those years.
So what age did you start to?
Probably around 23 years old, 24 years old.
Okay.
And I've tried it with all kinds of rocks. I mean, through the years, I've collected all kinds of different samples here. See, like here's a totally different piece of pyrite, so we could actually look at this one. This one's going to be a little harder to work with because, see, it's not just all crystals like that, see? This is a different lattice. Comes from a different part of the country. See, so now, if you want to go deeper into this, the magnetic fields of the Earth, where they vary, you get a different lattice. And this is like when they study rock samples and things like that, they're actually studying the past, what went on in the past.
Yeah.
You know, so.
But you found that iron pyrite is probably the best.
Well,
you get the best results with.
galena, iron pyrite. Let's see here. See, this is going to have a different.
Different color.
It's a different color, and its resistance is going to be totally different. Just going to do something different here. See, first of all, it's not to where it's tilting up. See, we can't get it. We can't. In other words, we can't here. We can't break enough of it away to get it solidly on the plate.
Yeah.
You know, to sit there and try to hold it. Oh, there we go. See? Totally different
Yeah.
pattern.
So once you know what you're doing, you
Yes.
can utilize those patterns.
Actually,
Yeah.
you notice it's more like this modified transistor.
Yeah.
See? And it means it has a high resistance in the emitter, because that's exactly what this has. So this is like susceptible to a certain frequency.
Yeah.
And what we're looking for is we want the energy from the universe to come in.
So you want the energy from the universe to.
Well, I want to use this as the crystal detector.
Yeah.
In other words, I want a one-way gate where I put up the antenna, and then of course the antenna lead, right? This becomes the device that captures the energy, and it can't ever flow back out.
Yeah.
It goes and it charges a capacitor, and then you just start tapping that capacitor off.
Yeah.
And that's basically what we were after when we were doing all this experimental work with the rock.
So Tesla got into this more in his later years than.
Yeah, and of course, he got into it where he said that he had found a way to build his energy machine that gathered vacuum energy through the use of semiconductive materials and lattices, which this is. This is semiconductive lattice structures. So it's a little bit different field to work with because you can't do much with this. This is already has its pattern.
Yeah, yeah.
And so you can only work with this pattern that's here.
Right, right.
Unless you want to grind it up and fire it in an oven to get it into a pattern that's more like this, where you have to use it for something. You can see it on the side here. You can see the actual material right here. That's semiconductor. See the copper substrate underneath?
Right, right.
But notice the color of it, it's gold colored.
Right.
Well, the gold sort of melts out of the material and coats the surface, and then the crystal grows in the gold.
How long do you have to fire it for?
About 15 or 20 minutes until it fuses. You can see the color of it right here.
Okay.
What's the anhydrite or something you've got? I wonder how that would be. So that's in crystalline
Calcium
form.
anhydrite, yeah, from drilling, you know, because I was really into
Yeah.
drilling.
Yeah.
And I knew which ones would chew the bits up and which ones wouldn't. And pyrites were terrible. They would chew the bits.
Oh yeah, because it's an oxide.
Right.
You're going to make sandpaper out of that. You know, now galena probably not too bad.
Yeah.
That's lead oxide.
Yeah. Yeah. Calcium anhydrite was toughen up bits.
Mm-hmm.
Still running it.
Yeah. Yeah.
Yeah. What does lattice mean? What is a lattice?
Lattice, crystal lattice.
Yeah, what is it?
A lattice?
Well,
It's the way
lattice
it
is
grows.
when you grow things over.
It's like
Yeah.
those carbon nanotubes.
Well, that's basically what it is. It's a lattice.
Okay.
It's the way the minerals grow in a lattice.
Oh, okay. I see what you mean. Yeah.
It's where they cross, you see.
Right.
There's negative resistors in this rock nobody knows. There's negative resistors. This is already a negative resistor. It's sitting out there as a negative resistor.
Yeah.
There's just nobody tapping the energy from this.
Yeah.
So you've already got the negative resistor right here. I don't know why you're trying to manufacture it.
Yeah.
Yeah, if you just learn how to utilize this right here, the negative resistor is already here.
Right.
It's cold. You don't feel it burning up. Now another thing too, see magnetic fields. Magnetic fields. Magnetic fields plays a very important part in this because this is the way the lattice grew. Where was it on the Earth? What state was it in? What longitude, what latitude? What was the magnetic field? What was the Gauss field in the Earth?
What kind of sunspots you were getting, and
Yeah.
yeah. Where was the moon?
Exactly.
Yeah.
At that time when this was formed. What was the actual magnetic field of the Earth? Because you can see that there's quite a difference between this mineral and this mineral. But yet they're both the same mineral. They're both considered pyrite.
This is more crystalline.
Yes.
Yeah.
Yes. It had a much better chance. This one here is a little bit more difficult to work with because if you look at it, you can see the structure is much finer.
Mm-hmm. It looks like gold in it too.
Yes, well,
This is what they
the
call
term
fool's gold.
the term fool's gold.
Right.
Right.
Well,
I don't know why everybody's climbing around looking for a negative resistor. It's right here. It's already done. Nature's already produced the negative resistor. All we have to do is tap it.
Yeah.
And that was what this study was all about. Well, I was looking for the negative resistance in the lattice. And fortunately, you find out that when you do all this, that you not only figure out that you can make semiconductors out of it, you figure out that you can actually transmute the metals that are in this to the copper substrate.
Mm-hmm.
Fire. 2,000 degrees, 3,000 degrees. See, everything just melts. And when it dries into a crystal form that's very fine. When it dries into a crystal form that the two are stuck to each other. Nothing harmful there, just ground up rocks.
Right.
You know,
You see, so that once looked like that, but after the fire hit it, this is what it looked like. And now you can take other minerals too. See, you can take these minerals, and they're totally different.
Mm-hmm.
See? But part of this mineral contains a material, when ground and added to this mineral, makes the lattices either further apart or shorter, wider or narrower, this band or that band. So you can see this here is basalt,
Okay.
and this right here is just a river rock.
so you tried them all.
I tried them all. I grind them all up, melt them, right? Mix them with a material that I can get a reading on. And because even T. Townsend Brown coated these rocks with silver and then measured what they did during the gravitational influence. They generated voltage for years. So see, the answer is really right here.
So you say he coated them with silver during a firing process, or he coated them
No,
ahead
he coated them, he had them specially coated, of which you could attach wires to, and then he built a special sensitive meter to measure what the output, this is where, I think he called it petrovoltaics,
I don't know.
petrovoltaics, where the rock's actually giving you the energy. See, you're quite capable of putting these things together somehow like this and getting energy between these 2 points, because batteries do it all the time.
Yeah.
It's just, do we have the measurement technique to get the potential between these two, as this is an insulator, see? Dielectrics.
Yeah.
Doped dielectrics is the answer to the free energy. The real free energy, because now I don't put any energy in. I just put up a wire, I hook it up, and bang, it fills my capacitor, and I charge my battery, and I have my free energy.
When you were saying earlier, there's no such thing as free energy.
Well, what I'm saying about people term free energy, the term is wrong. There is no free electricity. There is no free energy, because you have to work to get it. In other words, what you're terming free energy is a conversion from one energy to another energy that your meters can't measure. You're saying, oh wow, look, this new form of energy is doing this, but it's still costing you. It's still costing the universe. Now, the cosmic rays come every day to Earth, right? Why not just tap them? That's free energy. Draw the energy from the surrounding environment. That would be free energy. But it necessarily may not be electricity. It could be what Wilhelm Reich was talking about. It could be orgone. It could be a magnetic field deviation, where you go to that area and you feel good. Well, there's a new energy. It could be a piece of wood, a piece of metal, like Reich did, that he called orgone. It wasn't electricity. He didn't get any electricity from it. What he got from it was healing.
I think what the man in the street thinks of as free energy is he doesn't have to spend his dollars on it.
Right. Well, see, if you're looking for that type of free energy, then the only place you're going to get it's out of the air, because you already live in between two plates of a big capacitor. It's already charged. So you just need the material to cause the conversion process to electricity. Because you're walking around in it right now, and it doesn't feel like it's electricity to me. I'm just walking around just like this in space, right? And it doesn't feel like it's electricity to me until I walk to the right area and the two right materials, and I walk to the door and I get shocked. Then it's electricity. What can I do with that electricity? Well, I could store it. Use it at a later date. Well, what other forms of free are there? Well, if I stick two rods in the ground, I get two other forms. I can feel the current, but I can't read it on my meter. It's a different form of electricity. So I don't want to give anybody the impression that there's no such thing as free energy. There is. But what's the energy? Is it useful to you?
Yeah, that's a really good point. It doesn't have to
Is
be
it useful to you? Because if it's not useful to you, then why do you need it? You know, there's many things. I could pick up this magnet and go, gee, you can, look, one floats against the other.
Mm-hmm.
Is it useful to me? Can I use it for something? And as long as this does this where it stays apart, that's free. This is perpetual. Here's your free energy machine. Nobody realizes it. The minute you charge this machine, it's in a perpetual state of magnetism. This does not die. You and I do. We die. This magnet stays at your daughter's house and sticks the paper to the refrigerator. She dies, it goes to the little girl.
Okay, let me tell you something. I've got a magnetic clasp on my medicine cabinet.
Yes.
It's a little magnet that's
Right.
inserted into, and it's lost its magnetism.
It's probably an old Al Nico.
I don't know.
The only way a magnet can lose its magnetism is if it didn't have a keeper on it and it was an Al Nico. But this magnet cannot lose its magnetism. Now, take the Neo iron boron magnet, just get it warm and it'll lose its magnetism. As soon as it reaches its cured temperature, it's gone. Your free energy's gone. What can I do with a magnet? Well, let's see. What can I do with a magnet? I can do some things. Here, just give me a minute, Tony. I want to explain why I draw my diagrams that I always show these lines, and where I always show the magnetic field coming around these lines. Because I basically look at the magnet as sort of a figure eight, where these lines enter in the magnet, and the magnet has an intake and an exhaust. We're looking at this being the North Pole and this being the South Pole, and normally you see these field lines come out around the magnet like this.
Okay, so that's not two magnets together.
No, that's just one magnet. And basically I've always said that this one is spinning this direction, and this one's spinning this direction, and this one's spinning. And that sort of keeps the field lines apart, because we actually have these particles that are flowing in and out of the magnet in a perpetual state. And
Excuse me, particles of what?
particles of magnetic flux,
Okay.
which is energy of the vacuum, basically.
Okay.
And I always show a zero here because there's nothing there. And I always show a zero here. And then I always show a 0 here, which is an A, which we've already determined that this is the blotch wall. So basically, what we actually, this is just the way I visualize the magnetics taking place. Is we have the blotch wall. This is the absence of everything 0. And we actually have this. And this is where the vortex energy enters in to the magnet to provide the vacuum energy transfer for the magnetic spin. So I seen something that was kind of unique, and we've all wondered about these Faraday motors and how it could possibly switch, because a normal motor has poles, a north pole and a south pole, and one usually attracts in and one usually repels. So if we got a repulsion motor, then this south and this north is repelling this every time it's in the magnetic field. But these actual magnetic fields are spin this way. And it's where these two spins are opposite of each other, and so they repel.
Okay.
So you following me so far?
Yeah.
So, by the way, when I'm also looking at this, I'm looking at the vacuum energy, is if you're looking for a gravitational effect, it's here. It's out here. It's away. Because gravity is what's supplying this energy in. The absence of...
So you're saying that's an anti-gravity null?
Well,
there?
this is anti-gravity. When you look out here, if you were going to produce a gravity effect, it would be out here. It wouldn't be at this pole, and it wouldn't be at
Right.
this pole, and it wouldn't be at this angle, and it wouldn't be at this angle, it wouldn't be here, and it wouldn't be here. It could only be out here.
Right.
So, no matter if it's an electromagnetic coil, the effect is still out here. So if we were to look at it, we're looking at this.
Right.
We're looking at this here. Right out here. Now, something that's sort of phenomenal is I saw this little Faraday motor, and of course with neomagnets it made it really easy, where if we took this magnet and we put two magnets together, so this is the north, and this is actually a south, and then they're in attraction north-south, this is still the zero field. This is center point of the magnet. So we know that the vortex energy is entering in here at the blotch wall. And then of course the magnetic field is being incited by the gravitational energy. Once you charge this and you align the particles, this thing continues to spin. So these particles are really alive and they're spinning. So if we take this away, and we just took this magnet and we took a battery, and we put it here, and we took a copper rod and we came right in at this 0 point. we took this copper rod and shaped it like this, where it curved around. We took this copper rod and we shaped it like this to where it curved around. These live magnetic fields and the vortex energy that's coming in, once you set this motor up, it will continue to spin without switching poles at all. In other words, the polarity would always be the same. So here, as an example now, I'm going to run one of these for you so you can look at it for yourself. Okay, so here's what we got. We got one copper rod. And you can see that this is the way I bent it. And all we're going to do is we're going to put this inside here like this. We're going to adjust this until we get just the finite point of it. And then it's going to run itself as soon as I get it right here. I think they might have played with it. I'm going to get another battery because I think they played with it. Actually, probably the best way to do it is to take this. They put a little tit on here, Tony.
Yeah.
And you just take it off. So here's what the electrical thing is. It could be too that there's oxidation on it. I should probably clean it. It's been sitting a long time, Tony. See, the other thing too is that this is what they call a really high current motor. There's a lot of current involved in it. In fact, it's all current. But if you look at these things, they're like contacts.
Whoa, yeah.
There you go, man.
Wow.
So it's proven that these magnetic fields are actually spinning.
Hold on. Now, what have we got, John? We got a battery on top of another battery?
Yeah, you got a battery on top of this neomagnet. And notice where the contacts are. They're in the 0 point of the magnet. Because the 0 is the blotch wall. So you see the vacuum energy is actually entering in. And this is spinning in the vacuum energy.
And this is called a Faraday
It's
motor?
a Faraday motor, but...
Did Michael Faraday invented that?
Yes.
This is back in 18 or 17? Something?
Yes.
Yeah.
And my point is that if these magnetic fields were not rotating, this would go nowhere. So the magnetic field is actually out like this in lines, and right where this thing is right in the center of this 0. Right here where I have the two magnets together, the vacuum energy is entering in here. And as the energy enters in, it builds these magnetic field lines. Like I said, this is the way I believe it is. So it's actually 4 spins that this is operating on. So what's happening is we're putting a current on this magnet, and what's going to happen is these loops, this is one loop, like this. And of course this is coming across the 0 point, which is right here, right at the center of the magnets. where the crack is there.
Right.
See, that's where I'm telling it,
That's where you join the two magnets.
yeah, that's where you join the two magnets.
So the bottom part is two circular magnets
Yes,
together. Right.
right, and just one loop of wire.
Right.
So there's no brushes, there's no contacts. So how could it be spinning if these fields weren't actually going in opposite directions at the same
They
time?
fight each other, yeah.
Yeah. There's never been a satisfactory explanation on the motor. And I thought it would be interesting just to see this,
Yeah.
you know, where it fits into this theory of at the blotch wall of this magnet, because the way I see it, and explained it earlier, if you have an electromagnetic coil, you put the potential in, you put the positive on one side and the negative on the other side, and this folds down to produce a north and a south pole, but still leaves the blotch wall in the electromagnet. So, but remember, the electromagnet's pushing outward. So we don't have to have any vacuum energy coming in. What we want to do is we want to make this energy pump. So what we want to do is when we let this loose, we want this 0 point of the magnet to expand open, and we want to intake the vacuum energy like this. And then what we want the vacuum energy to do is couple in the coil and give that high potential, because we've done the conversion. And this is what we take and send to the battery. But this is a stationary item that we're looking at right here. And we know that for this to be a permanent magnet, it's been charged once, it's in a perpetual state of oscillatory action, meaning that it's constant, like it's a permanent magnet. It's not losing its magnetism.
How about the battery? What's
Well,
happening
the
to that?
battery is just supplying a current, which is completely different from the magnetism.
So really,
And so
that's,
there's really what this is a magnetic field without switching. In other words, no switching, no commutator action.
So what happens when the battery wears down?
Then it stops.
Okay.
But it goes for quite a while that way. And that's basically, I wanted to just show you that, to show you that my thinking is that the vacuum energy is what's causing this to spin. I'm not saying I'm 100% right, but it's worth investigating.
well, isn't this something to do, doesn't the quote-unquote theory of spintronics try to explain it in those terms?
Yes, they do. But I'm not quite certain that that's a perfect explanation for it.
Right.
So I find it kind of intriguing
Yeah.
that it even operates.
Because according to conventional theory, it shouldn't.
Yeah, it shouldn't, because this is just, here, it's one loop of wire.
Yeah.
And of course, put it on there and away it goes. But you have to have the wires just right, so you bend them up a little bit and then it doesn't want to operate by taking it off and on the magnet.
Right.
See, when you get it too tight, it's not going to go. It's basically like Pat says there, it's running around the battery now at an angle, but there we go. And once you get it adjusted right, it can just go as fast as it wants to go.
And presumably the more accurately
Yeah, the more accurate it is, the faster it's going to
No,
go.
I mean, presumably the more
Yeah,
vertical that vertical thing is, it's not going to wobble and,
right.
yeah.
The more accurate it's made.
Right.
Yeah.
It's actually speeding up. You can hear it.
Yeah. But it's kind of funny, it has to be right in this zero portion of the magnet to work.
Right.
Yeah, and we're running out of steam right now, but because the battery does get hot, does get warm.
Can you show us what's on the bottom there?
Nothing, just the magnet.
It's 2 magnets.
So it's an open loop completely. This this end is open.
But is this 2 magnets or 1 magnet?
Yeah, it's 2 magnets put together.
Can you pull them apart?
Hardly, but
Oh, they're that hard?
yes, they're
Okay.
Neo, so
I see, okay.
you see they lift their own weight.
Hold on. Oh.
You gotta get it just right, and then,
Well, you had it just right there for a while, till you pulled it apart.
yeah, see but the other thing too, Pat, is that the current is so much that it just arcs,
Yeah.
and that's why I did this.
Right,
Then it took off.
right.
See, it builds like an arc, like a burning point, and especially right here, see.
Degrades very quickly, doesn't it?
Yes.
What's the purity of that copper wire?
It's just regular house wire, just regular.
Which is what, 98%?
Yeah, somewhere around there. But you can see once it's operating correctly, it just accelerates
Yeah.
at light speed.
Yeah. I mean, why is it doing that? Yeah. I mean, that's
Well, if the magnetic
that's a really good
field,
question. Yeah.
If that magnetic field was that stationary, it wouldn't spin.
Right.
And so that shows you that these particles are actually traveling around the outside of the magnet. And notice it's at this 0 point.
Right.
Now, is that anything like the same technology as that Howard Johnson thing, or not?
No.
No.
So can this be converted into any kind of a commercial
Sure,
application?
this can be a motor.
An over Unity motor or?
Well, I don't know about over Unity or I don't know about under Unity with this,
Right.
but people have tried for years to do, I think the military is using the Faraday motor in submarines now as a drive. And that's sort of what I wanted to explain here was why I just do it this way. Because this is where I feel that the energy is coming from, out of the vacuum on these magnets. I guess that's all we need.
Okay, great.
And you can see it degrades quickly, Pat.
What do you mean, degrade?
Well, it degrades where it eats the copper.
Oh, yeah.
You know, and it's eating this contact. It actually,
Does it feel different inside?
yeah, it does.
I
It,
don't feel it.
well, it does. Sort of gritty.
I can't feel that,
Feel-
I believe you. Oh, that does?
Yes,
Yeah.
that's the major one right there, Tony. Because that's the pivot point.
Yeah.
Boy, you get a really rapid rate of degradation.
Well, you do when it's first new and the wires
Yeah.
shine. This has been sitting around for a while.
There's not an enamel on that wire, is there?
No,
Yeah.
no, this is coating with some kind of oxide.
Yeah.
See, because if I clean it, right, you get it just aligned just right.
Bingo.
Way it goes.
Yeah. It's a good shot. Like magic.
It is, isn't it?
That's a good shot. A weird shot.
Well, you can show all these things, right? Now we can actually, I think if we switch the magnet over, we can make it go the other way. Want to try that, Tony?
Yeah.
And the battery gets hot. I mean, you can feel the battery starting to warm up.
You turn, what do you
I
do?
turned it around. I turned the magnet around, so now it's going the opposite way.
So this is like the Coriolis effect or something.
Yeah,
We're now in the southern hemisphere.
yeah.
Yeah.
So you just flip the magnet at the
Yeah,
bottom.
flip the magnet around.
But the battery's
now.
the same.
Battery's the same.
Yeah.
So you got a forward and reverse spin.
And you couldn't push it to go the other way?
No,
Yeah.
Well, the Coriolis effect is probably the same thing.
That's what I said, yeah.
Mm-hmm.
Yeah.
That's why the water goes down the pipe differently each side of the equator.
right, you can't make it go the other way.
Right.
See, it won't go.
Yeah.
Right.
Now if we turn this over, and it goes the opposite
Yeah.
direction.
That is really, I mean, that really tells the tale, doesn't it?
Yes. Everything's controlled by magnetic fields.
Right.
And the oxidation is starting to build up.
Yes, and we're starting to lose our battery.
Yeah.
So I wanted everybody to sort of see this. And that's all it is.
Yeah.
Feel the battery now. It's starting to get warmer,
Oops.
right? It's warm.
Yeah, it is warm.
Yeah. So I'll go get a new battery and,
Okay, just change batteries
yeah,
because the old one was worn out.
just about.
So how long did it take to wear the battery out then?
Oh, we'll probably run it for a half hour or so there.
So this is a brand new battery.
Yeah.
Yeah, and that sucker's booking.
Yeah. It's also going counterclockwise now.
Yeah.
See, battery's heating.
So this battery's totally shot now.
Just about.
In half an hour.
So will it, by sitting and resting, will it become...
Yes, it'll pick
Yeah.
up and then we can run it again. Of course, as it oxidizes, it'll slow down.
Slowing down already.
Yeah.
It's slowing down now.
Well, it's eating the battery for lunch.
Well, is it essentially shorting the battery out?
Basically,
Yeah.
the currents has to be terrific around those loops to cause that kind of influence.
Right.
But I think it's basically oxidizing here.
Yeah.
Let's clean it and see. So let's just take it and clean it. Yeah, you can see right here, a little burnt spot.
Oh, at the end there, yeah. So it actually touches the center of the magnet?
It
or
sort
is-
of touches.
It has like a...
Yeah, it has
fraction of
like a
an inch,
very little contact.
very minute clearance to...
Mm-hmm.
Yeah. Okay.
There we go.
Off and running.
Magic. We'll just let it run. As it gets going. There's obviously no speed limit here.
Right.
So if you had the geometry precisely adjusted, it would go faster.
Oh, yeah,
Yeah.
exactly.
You can see it's kind of waltzing around on the top.
Well, it is. It's kind of finding its way around in that little hole at the top there.
Right. Got a bit of a speed wobble.
Yeah. Like the Earth, wobbling while it's coming around.
Right.
Precession.
Yeah.
So do you think this is what Howard Johnson might have been trying to invoke or capture?
Well, I think Howard Johnson was trying to utilize these magnetic fields that
Yeah,
are
that's why I
spinning.
asked, yeah.
Right.
Yeah. And this shows that they're really there spinning.
Uh-oh.
It just wears its contact out and then it's done.
So you just changed batteries just then?
No, I just scrape the contact. a
Oh,
little bit.
okay.
Do you ever have to scrape the contact on the battery, or is it?
No, you don't have to do it on the battery.
Just on the.
Yeah. I mean, that's one horrendous curve to do that. Because there's no switching. Both are just spinning around the magnet. Around the magnetic field. The magnetic field's actually going out like I drew it. And so these things are actually have spins to them.
Well, they're spinning down the axis of rotation, aren't they? As well
Yeah.
as spinning round the magnet. So they're actually spinning in three dimensions.
Yes.
Yeah.
Kind of neat, isn't it? It's kind of fascinating
Yeah.
that it even works. Better hurry up, I'll be cleaning the contacts. That's about it.
Yeah.
Now the heat will start to show up right in the center, Pat. You can
It
sort of
doesn't
see-
come immediately, does it?
No.
Yeah. Yeah, I can feel it.
Yes,
Yeah.
So what are you saying, John?
that the heat now starts to come out of the battery from the center portion of the battery. That's what Pat and I have been noticing, that the energy seems to flow from the center of everything.
You don't feel hot here and hot here. You feel it here.
Yeah.
Hmm.
And yet it's not. Oh, it is warm to the face.
Yeah.
Yeah. Not hot, but.
But it will
for,
heat in
for
a
a
minute.
battery.
So let's see if we can get some more heat out of it. It's the chemical reaction and it's coming directly from the center.
Okay.
So what you're saying is that the battery is not being used conventionally.
Right, it's not being, it's being actually shorted out.
Yeah. Whoop.
That's okay. It'll go. It'll just dance itself around.
Huh.
It's kind of unique.
Yeah.
See, it'll follow those spins. So really, what does this tell you? Which way is this spinning? What are the spins actually doing in this magnet? That's where I feel Howard Johnson was getting by trying to map all these magnetic fields so he could get the correct spin.
You know, the Earth spins a certain. Everything,
Sure.
all the planets, the Earth, everything, the Moon, they all spin the same way.
Right. There you go, Tony.
They all spin the same way.
It's like it's accelerating, see? I think we can get it.
Set it up again.
it actually gets going so fast that the centrifugal force pulls the copper apart. Pulls these two apart and then it gets off.
Yeah, because something's going on, because you've just got a battery there and you got magnets. And so something is imparting the spin to it.
Right. Now stop the camera for a minute. Now, do you want to try something else here? It's coming right from the center pad. You never know. See?
Oh, yeah.
So it wants to spin down here at the 0 too. See?
Oh, yeah. Yeah. Huh.
If I had a little bit longer wire, it'd be a little bit easier. You get the general idea.
Yeah.
That there's something going on in the magnet.
So hold on, you got your battery there, and then you got a spacer,
Yeah, just a spacer with a point.
and then you got your neo. One neo?
Right, one neomagnet there, see? And then
Right.
I'm just
And
touching it,
you're
see?
touching it at the midpoint.
Yeah, and see it spin?
Oh, yeah.
See?
Yeah.
So as long as I touch it at the midpoint, it just takes off. So as long as I can make a contact. It's kind of hard to do with this one.
Yeah.
Not really long enough. There we
There
go.
you go.
See, that's really going.
Yeah. Huh.
Now, why is it sitting there spinning, see? If there's something not spinning in the magnet. It's kind of unique.
And that, yeah.
Isn't that weird? I thought it'd be interesting.